The models we study for applications in finance are not just mathematical constructs. They're tools that we use as approximations to reality and that we use for interpreting data and understanding the world around us. Now in finance, the problem we have is quite different from that we have in the physical sciences, even though some of the mathematical tools are quite similar. Rutherford once said that if your experiment needs statistics, you should have done a better experiment. But in finance, we're really quite different from laboratory sciences. Most of our data is noisy. We need statistics. We need tools to get to the bottom of it. Furthermore, we can't repeat an experiment, not in a true laboratory sense. Actually, we have an interesting dichotomy. We've got, on the one hand, that we often deal with market data and historical market data, and that is almost by definition reproducible. If we plug in the same numbers, we should get exactly the same answer, no matter who does the calculation. That's a good reason why it's an interesting exercise to pick up previously published papers and work and reproduce their results. Unlike a laboratory result, you should be able to get exactly the same thing if you can get your hands on the same historical market data on which some empirical studies were based. On the other hand, markets change. We can't go back in time, and all of our results are going to generally be provisional. So this leads to a different perspective on modeling and often to difficulty in settling questions. And one that we'll take a look at is going to be the role of the random walk model and the so-called random walk hypothesis. What does it say, and can we test it? More generally, when we're looking at models, we have a bunch of questions that we want to ask, and I'll talk about a few of them now, and we'll develop more of them over the course of this lecture and beyond. What we'd really like to know would be, what's the model that generates the data that determines how prices move, how variables evolve, and so on? But nobody tells us that there is such a thing. There might not be such a thing. If there is, it might change, and we can't look it up in a book exactly. What we're typically faced with when it comes to real-world problems is data, and maybe a whole bunch of different models and some candidate models. So the questions we ask include these, and not necessarily in this order. What's the model that best fits the data if we have a choice of models? If the models have adjustable parameters, how should we find the best values for those parameters? How do we decide among the better of two models that might have a different number of adjustable parameters? Do the models obey stationarity? That is, do they describe the evolution of our variables of interest in a way that the models themselves don't change over time? That is, the probability distributions are stationary over time. They're so-called times translation invariance. How should we be estimating our parameters? How can we take a look at what's going on with data? Before we build models and test them, we might want to take a look at the data and see if there's some general attributes that suggest the kind of models that might or might not be appropriate. So we often do some initial exploration. And sometimes we do this with the same statistical tools that show up in other settings as well. We often want to test hypotheses. Is this model correct or is it not? That's our simplest version. Or if we have a bunch of models, which of the models is the best? And finally, we'll take a look when we look at structured models of information propagation in time series models as to how we can decide about what the appropriate correlation lengths are, what the distances are, what the order and class of an appropriate model is. And there's not always an easy answer. So let's review for a moment just a couple of the basics. You know from statistics that a statistic is a function of the data. It's a formula into which we can plug numbers and get out another number. And the classic examples, and two of the most useful ones in finance, are the mean and the variance. So the mean, we take a bunch of numbers, compute their arithmetical average. That's a function. We could have taken other functions. We could have taken their sum. We could have taken different weighted averages. This is a particular statistic that gives us a summary number given a time series, or a collection, actually not necessarily ordered, of values r sub t. Same thing for the variance. We can compute this. Now, descriptive statistics don't require a model. And one thing they do is they reduce a large number of values down to a small number of values. So these two numbers, mu and sigma, can characterize a set of r's of arbitrary size. So that obviously means that we're throwing away information. We're going from a large number of values down to 2. For these to be useful, we should, in some sense, capture values that matter to us for what we're doing, in the sense that if we had 2 different collections of R's, 2 different samples that were taken, and they had the same summary statistics, we've got a good collection of summary statistics if we feel about the same. In this case, we often think of mu and sigma as being the mean return and risk associated with an investment or an asset, and 2 assets that had similar mu and similar sigma might be things that we would feel similarly about. Whereas if one had twice the return of the other for a given level of risk, we would differentiate them without needing to dive into the details of the R's. So that's a sign of well-chosen and well-behaved statistics. But this is purely descriptive, and it doesn't require any kind of model or anything further. An estimator is a random variable, and the formulas for estimators look quite familiar. These formulas here for an estimator for the mean and for the variance take a form that is mathematically identical to what we saw on the previous page. However, we think about them differently. In this case, we don't yet have the data. We think about them being a function of future observations. So they're random variables in the sense that given a particular set of realizations, a particular set of draws from a distribution, we'll get different values. So mu hat and sigma squared hat may take different values based on different observations. So as a random variable, an estimator has a distribution that's known as the sampling distribution, and the first and second moments are easy to compute and derive. And because of the central limit theorem, if we've got well-behaved estimators, then we run into the situation that we might expect, where the distribution, the sampling distribution, can approach a Gaussian as the number of observations gets very large. So that's one of the reasons that we like large statistical samples. We have good statistics. It gives us not just a narrow distribution, but it also gives us one that has a well-known shape. It approaches the Gaussian. An estimate is a number that we get from the same formulas by applying it to a particular set of realizations. We use these to estimate parameters. So for example, in the random walk model that we wrote down, we had 2 parameters, the generalized random walk, we had 2 parameters, mu and sigma. When we did Monte Carlo simulation, we picked values of mu and sigma and generated a bunch of concrete numbers on the computer. But suppose we start from data and we'd like to know what should we use for mu and sigma if the data were generated from, say, the random walk model, what would be the right mu and sigma that would correspond, that would have generated the data? And the answer to that we can find from usual statistics, from maximum likelihood estimation. And in this case, we find the mu from the average and the variance from computing the sample variance of our set of observations. Now, a quick aside on some things about doing financial returns in particular, because that's the dominant case where we're interested in finance, where we're looking at time series analysis. The usual things that we would see in investment reporting are going to involve simple returns, monthly returns, annual returns, and variances or volatilities may be computed using the simple returns. But often mathematically, it's better to work with logarithmic returns, continuously compounded returns, rather than simple returns. Now, it's easy, they're one-to-one connected, because the simple return is just, I can exponentiate the logarithmic return and subtract 1 and get the value that I need there. And for a lot of applications, numerically, the values are really, really close. For example, if I'm looking in the equity markets and I'm looking at returns over a one-day time scale, the numbers, the typical size of the returns is very small. And mathematically, these will be quite similar. But if we want to do things right, we need to use the correct formula. These have exactly the same information, and we can compute the expectations by changing variables in whichever form is more natural for us to compute. To show you the point I made just a moment ago, if we look at a Taylor expansion of big R in terms of little r, of simple returns in terms of log returns, or if we turn it around the other way, we can see that the leading order big R and little r, they're the same. However, there are two things we want to keep in mind. One of them is the deviations can be economically significant. So if we take a look at things like a typical 10% return with 30% volatility on an annualized basis, if we look at the formulas, we can see that there are deviations depending on which of the formulas we use to compute them. The other thing to keep in mind is that this is great when the values are small, which they are most of the time. But when they're not, they're not. So when we have a day like the stock market crash in October of 1987, where the market fell by a quarter in a single day, whether you're using logarithmic returns or simple returns makes a big deal, and the higher order terms in the Taylor series matter. So it's always better to do it right. In practice, we can sometimes get away by not taking a look at the difference depending on what the applications are. When we're thinking about volatility, though, and we'll see this when we get to the Black-Scholes equation, when we think about option pricing, one of the important parameters in the model is the volatility of the underlying. And that is something that we need to estimate from data. So what should we use for our estimator? Our idea is that we ultimately need to have a good model. So there are a lot of different possible ways of estimating, and what we really want, the real test, is whether the procedure that we use produces good applications of the model that ultimately fit the data in the markets properly. The typical approach, though, is to use logarithmic returns, not simple returns, because they're consistent with the formulation of the model. That is, within the option pricing models, as we'll see, there's an assumption that the returns are log normally distributed, or in other words, that the log returns are normally distributed. If we start from the parameters of the price process, that if we think of the price as being the price from the previous day times the exponential of some logarithmic return, and then we think about iterating that, that's consistent with our random walk model here. Now, the drift coefficient cancels out of the definition of the variance, but it is required for our estimation of the volatility. Remember that the computing the volatility or computing the variance requires looking at the deviations around the mean, and the only mean that we have we're going to need to estimate from the data. There are in the literature lots of alternative estimators that have different benefits. They have improved efficiency, and they take into account some things that we might not see simply from looking at close-to-close returns. And a couple of them, like the Parkinson and Garmin class estimators, take into account additional information that sort of interpolates between the discrete observations that are usually made for computing returns from the close of one market day to the next, including did the price, where did it achieve a high or a low during the day, intraday, and do we take into account the open close, high and low during the day? And that additional information can be helpful. So ultimately, these are modeling choices we need to see, but the starting point usually is the traditional estimator that we looked at before. Now, when we look at hypothesis testing, the simplest case is taking a model like the random walk model and asking whether it's right or wrong. So hypothesis testing is the simplest case. We start with two hypotheses, a null hypothesis and an alternate, and we define a test statistic to see if we can reject the null hypothesis. This test statistic is a random variable. So we often do this probabilistically. In classical statistical inference, we think about a p-value, or we look at a z-statistic, and we say if the null hypothesis were true, what's the likelihood that we would observe a test statistic like this, or that's this extreme or more. That is, we look to see how small the p-value is for evidence to reject the null, and we compare it to some significance level that we've hopefully agreed at in advance. Because the test statistic is a random variable, it's drawn from a probability distribution, and if we have a lot of observations to make, we can rescale things so that it looks close to a normal distribution or a related distribution. Just to keep in mind a simple example before we turn to the random walk, imagine that we're flipping a coin to see if it's a fair coin. So we take a coin, we flip it 10 times, and we observe a bunch of heads, and we ask, is the coin fair or biased? If we don't know in advance whether it's fair or biased, we might imagine that there's a particular probability of observing heads, and we could ask, what's the value of p and what's the best estimate for p? And if we do have an estimate for the bias, how precise is it? How much confidence do we have? But simple hypothesis testing starts with two hypotheses. H0, the null hypothesis that the coin is fair, that the probability is 1/2. The alternate hypothesis that it's anything other than 1/2. Question to think about in any of these cases: what are the appropriate test statistics that we might choose from? Let's look at alternatives to the random walk. If we analyze market data, for example, for stock prices, in the style of Lowe and McKinley doing a variance ratio test, one of the ways that we can see that the random walk model is not a good fit for the data is the presence of serial correlation in returns. That is, we see that the returns are not, in fact, independent. If they were independent, the scaling behavior as we add together more and more terms would grow, the variance would grow linearly with time. And if we observe departures from that, that doesn't just mean that we reject the random walk, it gives us a clue as to what we might want to use to replace it. So if we're constructing aggregating returns, say Q terms at a time, if they're not independent, then when we compute the variance, the cross terms don't vanish when we take expectations. And that's telling us something important. That's telling us that information is propagating from one step to the next. So we want to think about autocovariance and autocorrelations, which measure the relationship of a time series with itself. That's what the auto means. And we just shift in time by k time steps. So we want to do this in two ways. One of them is in expectation for looking at unrealized, unobserved variables in the future. And the other is we'd like to look at estimators for these properties based on past data. And of course, we'd expect these to be related. So the definitions that we have are going to be, and our notation will be gamma k for the covariance between two R's of different lags. When we have a stationary process, the key thing is it should only depend on the difference between the time indices. So t minus k is k, and that's why I put the label over here. Notice that gamma k doesn't depend on t. It only depends on the time difference, on the number of steps between the two arguments. In this case, rt and rt minus k. Gamma naught is when I set k equals 0, and that's the covariance of rt with itself. And rho sub k is just a normalized version where I divide by the variance, in the same way that we usually compute the correlation of two random variables by dividing by the square root of the product of the variances. If it's the same variable, if it's an auto covariance, and we want to get the auto correlation, we divide by the square root of the variance twice, variance times variance of the same series. If the series is stationary, that's equivalent to just gamma k divided by gamma naught. And this will be normalized. This will be a pure number, whereas gamma has units of r squared if r has dimensions. So for instance, if we think about a sum of two one-day returns, the variance, if they were uncorrelated, would be twice the variance of the one-day returns. But if they are correlated, there's an extra term. So the variance of a two-day return, which is, let's see if I can get my pointer back. Well, if not, we'll use our pen. The variance of a two-day return, which is just the variance of two consecutive days, is going to be twice the variance. It's going to be the variance of RT plus the variance of RT minus 1. It's stationary, so those are identical, plus twice the cross term in expectation, and that's going to be the covariance of R1 and R2. So we can write that as twice the variance times 1 plus rho 1, where rho 1 is the lag 1 autocorrelation function. That is, it's the correlation of RT with RT minus 1. So this is going to be bigger or smaller than twice the variance of a single period return, depending on whether the autocorrelation is positive or negative, depending on whether the return in one period is more likely to have the same sign or the opposite sign of the return in the previous period. So in order to estimate and compute, we use our usual formulas for computing covariances of statistical data and for computing correlations of statistical data, with one caveat. Normally we take two time series of equal length And to compute their covariance, we subtract off the mean of each one, we compute their products in each time period, and we sum over the time periods. We have a little bit of an issue when we look at finite length observations from actual historical data, in that suppose we have a series of 100 days. If we shift by one, they'll only have 99 days in common. There will be one off the front and one off the back. So we need to adjust. And as we increase the lags for a given data set, we're going to have shorter and shorter lengths in common. So we need to be careful of that we don't run out of data and that we look at the common period. Usually we make sure that we have series that are long enough that the endpoints won't matter, that there'll just be small deviations, but we do need to check that. Alternatively, we can require that we have data of a certain minimum length by saying that we need to have a certain number of common points, and then we can account for the overhang for the lag. So if we want to go up to lag 20, which we would rarely need, we'd want to make sure that we have enough for 20 points overhanging at the beginning and enough points in the middle after we chop off those points. So the formula we have really is just very much like the formula for computing the covariance of two random variables. Subtract the mean, subtract the estimate of the mean. These should be the same, but we usually want to compute them appropriately for the length of the series it enters. So because we're not using exactly the same data series, because of the offset, because some points are missing, we want to use the mean for each series. So it's removed. We subtract off the sample mean for the data set that's there, and we compute. Now, we expect in general to see convergence depending on the details. So as t goes to infinity, or as we take a very large number of points, this estimator should converge to the true gamma k, and the sampling distributions, we can see convergence in square root of t by choosing to resample things, to rescale things, so that if we want, we can think of the errors or the deviations appropriately scaled by powers of t, so that they are drawn from a standard n01 distribution if we'd like to apply that in a hypothesis testing case, and we want to take a look at usual confidence or significance levels like plus or minus 2. Now, when we observe autocovariance, what we're looking for is the direction and the magnitude of departures from a random walk, and we'd like to know how large the correlation is from one period to the next. So serial correlation is a typical analytic and statistic that we'll run when we get a time series of returns. It's an important attribute. After we've computed the mean and the variance, one of the next things we'll almost always want to take a look at to characterize what's going on is the autocorrelation or autocovariance functions. So in our example of 2 time steps for lag 1, we compute this, we have this expression, and what we can do is we can compute a variance ratio where we can compare our variance over 2 time steps to what we would have expected had it been a random walk. This would be 1 under the hypothesis that it is a random walk, and deviations from 1 means we have deviations from random walk behavior. If it's greater than 1, we have positive serial correlation. If it's less than 1, we have negative serial correlation. And we can generalize this to higher steps, and we can get an expression. We can show with a little bit of algebra that we can express things as a sum, a weighted sum of the different autocorrelation functions at different lags, all the way up to value q if we're looking at aggregating q steps at a time. So we'll typically look at all lags. Usually the first one is the one most of interest. But in principle, we can look at this at any lag and any separation. So what are some alternatives? Well, we've seen a couple of them already. If we have deviations, we might think about adding extra terms to generalize or extend the random walk model. And the class in which we can look at are ARMA models or even ARIMA models. But ARMA models include a combination of autoregressive terms that depend on previous lagged observations of the random variable, and moving average term that depend on the previous lagged shocks or innovations, which are not related to the actual direct observations themselves. So in our language, we can add r's lagged on the right-hand side, or we can add z's. And of course, they're not entirely independent if we want to trade them off at the possible cost of doing an infinite recursion. So some models that we've seen: random walk model with no extra terms, AR1, with a constant term, a z term, and then one lag. A generalized ARMA PQ model where we've got p lags of the r variable, q lags of the z variable, and in each case we have our increments, our z's, written here, are normalized IID random variables, which makes it easy for computing our expectations. Coming back to our old friend, the AR1 model, we can write it in sort of standard form, and we can look at its structure, and now we want to think about what this is telling us relative to the random walk. So we look at the mean return. The mean return is 0. And remember, lambda equals 0 is the special case where we get the random walk. The variance we compute by putting in the equation. We substitute here for the definition. We put in our equation as a reminder. And we take expectations and we solve algebraically. And we find that we have the variance is sigma squared over 1 minus lambda squared. We get the higher order values by recursion, and we know that the values as a function of k are decreasing. Each extra k, each extra lag in the AR1 model brings the power of lambda. Since lambda is less than 1, that's suppressing the magnitude of the fluctuations. So what it's telling us is in this model where there's mean reversion, that influence on a given day above or below the mean propagates in time but is damped out exponentially. That would be the end of the story if there were no sources of randomness. But because we can get new kicks every day, this exponential decay may not be as easily visible in the data. So we want to be able to estimate things from data, and we want to be able to determine which is an appropriate model to use from that large class. Is it AR1 or is it an ARMA 3-2 model? How can we tell? How do we pick the appropriate order of a model? And within each model, how do we determine its parameters? So when we look at estimation, we want our estimators to be consistent. That is, in probability, they should converge to the true value. If I take t to infinity, if I look at enough points, then the probability of deviating from the true value should vanish. This is equivalent to our law of large numbers. We want them to be unbiased. Unbiased simply means that the expectation of the estimator should be the true parameter value. We want them to be asymptotically normal so that we can, and we expect them to be asymptotically normal so that we can apply our tests. And this can be shown for the estimators that I've written down so far. Typically, we need to think about the sampling distribution, and we'll choose scaling variables so that we can relate things to a standard normal distribution for significance testing. And if we have estimators who do all of the above and we have more than one choice, we'd like to find the best estimator, possibly one with minimum variance, and we can talk about efficiency of estimators to give us the best estimate with the within a given class. So how do we do parameter estimation in AR1? Well, AR1, we have a structure. We have 3 parameters. We have mu, lambda, and sigma. And what we want to recognize is that it really has the structure of a typical linear regression model, and we can find its parameters using ordinary least squares. In fact, the only thing that's special is that we have an r on the left and an rt minus 1 on the right. Now, when we computed the autocovariance, I emphasized that those are really the same series. It's a stationary series, so their expectations are the same, and we can think of them as being the same. When it comes to estimating the parameters, I want to take the opposite tack. Let's think of them temporarily as being completely different. So remember, if we have a model that looks like this, we'd like to do a linear fit. We have a typical regression model, and we add an error term if we don't have points lying exactly on a straight line. We'd like to find a line of best fit that is where the errors are minimized for the best values of alpha and beta. We can get exactly that same structure from our AR1 model just by doing a little algebra and shifting terms around. So if I move the r minus mu and I move the mu to the right-hand side, I can write this as RT is a constant plus something times RT minus 1 plus an error term. So that looks exactly like the above if I make the substitutions for alpha, that's equivalent, the intercept is equivalent to mu times 1 plus lambda. The slope is minus lambda. The y variable, the dependent variable, is r sub t, and the independent variable is r of t minus 1. So given data, we can just apply ordinary least squares to get the values of the coefficients. So we can do that ourselves using ordinary least squares in a spreadsheet program or in R using the LM function. R also has some nice special functions for computing AR and for ARMA models that we'll get that directly. But the basic idea is that we already know how to do this. It's just ordinary statistics. Now, we can do exactly the same thing for an ARP model. We just have a bunch more terms. So we use our maximum likelihood estimators. We can throw it into a spreadsheet. We can throw it into R. We have a multivariate regression. We turn the crank. We get our usual estimates. How do we determine the order, though? Suppose we're not sure what P to use. Suppose I don't know if it should be AR1 or AR3 or something else. So the tool for doing order determination for autoregressive models is through what's called the PACF function, or the partial autocorrelation function. And the idea is really straightforward. What we do is we set up a sequence of models, and we do an AR1 model, and we do an AR2 model, and we do an AR3 model, up to an ARN model. And I've written these down here, okay? So for each of these models, we do an estimate. So I do my line of best fit for the first model. I do my line of best fit. So given the same set of observations in R, so the same time series data for R, in each case, I do my line of best fit. And the PACF is defined to be the coefficient of the last lagged term. So in this case, it's C11. In the first one, in the second one, it's C22. And the last one, it's CNN. And what we want to do is we want to identify how far we go when we no longer need to add new terms. That is, when the last coefficient is negligible, then we drop it. So the PACF function is very convenient for capturing all of this at once. We compute all these regressions in parallel, and then we can take a look. And what we want to do is we're saying there could be more terms, as we generally do when deciding how many variables to choose. We want to have an economical, parsimonious description of the data. We're going to pick the smallest number of variables to give us a meaningful description of the data, and we're going to toss out extra terms that are not needed, where their coefficients are not significant. So let's look at this for a couple examples. I'll generate some Monte Carlo data, and here's my Monte Carlo data for an AR2. So you can see that here. These are my parameter choices. And here is my AR2. So I've made a bunch of parameter choices for C0, C1, and C2. I'm going to look at 1,000 time steps. I'm going to compute a single path here, but you could certainly compute more. I'm putting this in a column vector. If I had more paths to do in parallel, I could easily do that. I'm going to run a recursion starting at time step 3 because I need some initial observations, which I'm going to set equal to 0. And I'm going to run my recursion. So RT, this is just my defining equation for an AR2. And then I'm going to plot a path. So here's my path. And then I'm going to look at the ACF and at the PACF. And rather than computing them by hand or doing them in Excel, we'll do it in R because this will give us all the results in one fell swoop. So here's an example of what my sample path looks like. You should run the code. Your sample path is obviously going to look different. And here's the AR2 sample autocorrelation function. So remember that autocorrelation functions, unlike autocovariances, are normalized. They're pure numbers. So they're normalized. The lag 0 should be equal to 1, and we see that here. Okay, we see that we've got things showing up at lag 1 and at lag 2, which is not surprising given the structure of our model. And then we take a look at the partial autocorrelation function. And we see that we have non-negligible terms for lag 1 and for lag 2, and everything else is not statistically significant. So this is an example of how we can determine the order of a model when we have potentially different numbers of terms, how we can estimate the parameters for a given model of a particular order using ordinary least squares or maximum likelihood estimation more generally, and how we can extend the random walk model to a range of models that have positive or negative serial correlation and that potentially allow us to describe interesting ways in which information can propagate from one period to the next. Now, when we add more terms and more parameters, we can improve things by getting a better fit, or it may lead to overfitting. So typically, this is an old story in statistics. We want to expand the likelihood function with a penalty for additional parameters, because we like to say that if you can have the same quality of fit with different numbers of terms or different parameters, we'd rather have fewer. So we penalize extra parameters and in the likelihood function, and there are a couple of common ways of doing it. The AIC and BIC that give slightly different penalty weights, but the general idea is that we can, in modeling, we can favor simpler models with fewer terms. Sometimes, as in the previous example, it will jump out at us and we'll be able to see where to truncate the series. Sometimes the data, unfortunately, will not be as clear. Forecasts with time series models are predictions about future observations, future realizations of our random variables that are conditioned on information that's known at the time of the forecast. Now, what is a forecast? Well, the output could be one of a number of different things. It could be a point forecast. For example, the price of Tesla stock in 30 days, a specific number. It could be a probability forecast. Probability of rain this weekend is 30%. It could be a full distribution. That is, we might say the probability of stock XYZ, its return distribution over the next year is log normally distributed with a mu of 10% and a sigma of 30%. So any of those could be the output of a forecasting process. And of course, we'll want to evaluate the quality of forecasts. And in many ways, it's less dramatic or mysterious than it might seem. One of the attributes of a forecast is that it has a horizon, or it may have multiple horizons. That is, a forecast is framed in terms of 2 points. The point at which we make the forecast, and that we need to know so that we know what information is available on which to base the forecast, and the future date when the realization will be known. Clearly, we can't judge the quality of a forecast until that date passes, and then we can compare our predictions with the subsequent observations. So we usually think of a horizon, and as time progresses between now and the horizon, unless the horizon is 5 minutes from now or the next day, if there are multiple steps in which we could update our horizons based on new information evolving, the forecast could change. We may have rolling forecasts. We may have forecasts where we move both the current time and the deadline, or very commonly, we have forecasts for a particular date, an earnings release date, an end of a fiscal year, or picnic weather for this Sunday, where as time evolves, we may be interested in the same terminal date, which may be fixed on the calendar, but we have new information that arises and we can update our forecasts. So if I said that our chance of rain for Sunday is 30%, perhaps yesterday I made a forecast based on what I knew at the time, and I said it was 0, it wasn't going to rain, and tomorrow my forecast might change again. Perhaps it goes to 50% as new information comes along. In time series models, we want to know what's available, what's the information set, and now we're going to use the same machinery that we did in solving models in closed form unconditionally, but now we're going to condition on information that's available at a particular point in time. And here's where the lag structure of models, such as AR and MA models and ARMA models more generally, come in. So let's take a look at an example. Let's look at the AR1 model. So here, for convenience, I've simplified our usual AR1 model by defining a new variable y, which is RT minus mu divided by sigma. So I've taken our usual defining equation and I just divided it through by sigma. Now this looks like a normalized random variable, but remember, that's not necessarily the case. Sigma is not the standard deviation of R, it's just the coefficient we put in front of Z in our model. So this is scaled to be dimensionless. It certainly looks like it might have 0 mean, and some unit 1 size variance, but that's something that we would need to compute. We can't just infer that from here. The reason I defined it this way was to clean up and reduce some of the parameters so that we really only have one parameter left in our model, lambda, and we can put the others back by resubstituting for y using this expression. So in terms of these variables, the AR1 model takes a simple form. Y sub t is a new random term, z sub t, which would be all we'd have if it were a random walk. And if it's autoregressive of order 1, we have a coefficient, which here is called minus lambda, times the previous observation, y of t minus 1. If we're forecasting, it's helpful to shift our thinking from looking backward to looking forward. So let's just add 1 to t and write it in this way, which is a little bit more suggestive, if not more informative. Let's say that yt plus 1, the next observation we're going to have, is the next realization of the random variable z minus lambda times the last known observation, y sub t. Now, suppose we were to compute the conditional expectation based on the information set available at time t, which I'm going to denote just I sub t for the information set. In this case, it only consists of the past realizations of y because those are the only variables in our problem, but it might exist of a bunch of auxiliary, financial, or other econometric variables. So in this case, what I wanted to do is take an expected value, assuming that I know all of the realizations up through time t, so that y sub t is no longer a random variable, but everything yt plus 1, yt plus 2, yt plus 3, and so on into the future, those have not yet been observed, and they are random variables. So exactly how I denote this is a matter of convention, and these are my conventions. So hopefully the idea is clear. Let's take a look at what the consequences are. When I take expectations of both sides of the equation, on the left-hand side, I have the expectation of y conditioned on the information set I sub t. On the right-hand side, the expectation of z is 0 because it's a standardized random variable. Its value, its expectation is always 0. And this term now is a constant, okay, because it's already been observed. So its expectation is just equal to itself. So it's minus lambda times y sub t. How do we find the forecast or an expectation 2 steps in the future? We iterate. So y sub t plus 2 from the defining equation for the AR1 process, I can just take the previous equation and write t the same way I replace t by t plus 1. I'll replace t plus 1 by t plus 2. So I have this defining equation, y of t plus 2 is zt plus 2 minus lambda yt plus 1. Now I'm going to substitute my previous equation for yt plus 1, and I can, just by substitution, I can now express yt plus 2 as z of t plus 2, which is in the future, minus lambda of zt plus 1, which is also in the future, plus lambda squared times yt, which is a known quantity. And now I'll stop. Take expectations of both sides. The first 2 terms vanish because they're z's. They have mean 0. And the expectation for 2 steps ahead in our process, conditioned on the information available at time t, is equal to lambda squared y sub t. When we look at forecasting, there are a number of different elements that come into play. And I would just like to lay them out for you, but we're only going to take a look at a small subset of them. Forecasting is a very big subject. We're just going to touch on it in the context of time series modeling applications so that we can see how we take the structure of our time series model and construct specific forecasts based on given information sets. So what are the elements of forecasting generally? Well, first, we'd like to know the nature of the process. Is it something deterministic? If it's given by a known curve, a sine wave, or parabola, we can predict exactly where something's going to be. We can tell exactly when the next eclipse of the sun is going to be. We know exactly when the next eclipse of the moon is going to be. We can even send spaceships to land very precisely or send them through the solar system because we have deterministic processes that we can solve. If we have random processes, we don't expect to get that kind of precision. We're going to have necessarily probabilistic forecasts. The processes could be stationary, they could be non-stationary. We're going to have very different tools for predicting them in those cases. And are they laws of nature or are they human behavior? If they're laws of nature, at least we know that the process itself doesn't depend on circumstances around it. Human behavior could change at any time. How much do we know about the process? Do we know the process, or do we not know what the underlying process is? Perhaps we know the process, we know what it is, let's say an AR1 process or an ARMA1-2 process, but we don't know what the parameters are. So in one case, we have to figure out what model to work with. In the other case, we may have uncertain estimates of the parameters which we'd like to apply, and that will be an additional source of uncertainty in our forecasts compared to the case where we know the parameters. And is this a theoretical model that's based on some financial or economic ideas, or is it an empirical model that's just fit to the data and it seems to work, or is it a theoretical model that should work? We have the sort of normative and positive views of things. And although the approach is going to be the same, the way in which we'll think about evaluating the model quality will be different, because to the extent that we observe deviations, it will tell us something about our assumptions and what we would need to revisit and how we would then refine things. If it's an empirical model, we may need to get more data or a better data set, or we might need to find a better model to fit it. If we have a mismatch with a theoretical model, perhaps we need new ideas. Perhaps the ideas that we thought controlled the processes that produce the variables were just wrong, or in need of some extension and generalization. How complex is the model? The examples we're doing are mostly going to be univariate models or bivariate models. So we could have a very large number of variables, and they could be coupled. Typically, when we think about multivariate models, we look for ways that we can simplify them and reduce them to previous cases. So it's often possible by taking linear combinations to take a multivariate process, particularly if it's a linear model, and reduce it to a series of uncoupled separate linear models that then we can solve. But the techniques will depend, and linear is usually fairly straightforward category with some reliable tools that we can regularly deploy. Nonlinear is kind of an open category where there's no guarantee of success, and there's not necessarily a general approach. Those are not the most common models that we'll see in finance, and those will not be among the things we'll be looking at in our future discussions or in any of the problems and applications. We do want to think about what the horizon is. Do we need one step ahead? Do we need multiple steps ahead? That is, would we like to produce at every possible future horizon? Does it go off to infinity? Do we need asymptotic results as t goes to infinity? Or perhaps, as in many financial applications, we have a finite date. We have the maturity date for a bond, we have the ending period for a loan, we have the expiration date for an option. And in those cases, we might be interested in forecasts over only multiple steps, but maybe only over a particular horizon, which decreases as time evolves. What are the forecast criteria? Are we actually forecasting observable variables or not? That might seem strange. You might think, of course we forecast observable variables. But keep in mind that one of the things we've already seen is models where we introduce volatility as a parameter. We have sigma, and if we take a model of time-varying volatility, we need to keep in mind that volatility, while it can be a parameter in a model, is not an observable quantity. We can ask what the price of an asset is. We can't ask what its instantaneous volatility is. To know its volatility, we need to observe it over a period of time. We measure the random fluctuations, and that quantifies what the volatility is. But if we have a model of dynamic volatility where the volatility changes over time, there are many such models. They're very important in finance, but we can't directly observe the volatility. So we need to do some extra work to be able to connect the predictions of the model with things that we can observe so that we can compare predictions to outcomes, so that we can compare forecasts to observations. We'll want to think about measures of forecast accuracy. How close is close enough? If we insist on a point forecast being exactly right, most of our predictions are going to be exactly wrong. But usually we'd like to have some measure. And one of the important things to keep in mind in finance compared to other areas where we use statistical methods and we make predictions and we make forecasts is that we often have a very real cost associated with error. So the usual things in the literature like mean squared forecast error are convenient mathematically, they're somewhat intuitive, but in finance we often have other numbers in mind, like the loss in a particular scenario, the financial loss, which might not be the same easy to use mathematical expression, but we do want to keep track of the fact that the economic cost of an error or a deviation, or the benefit, if it's a deviation on the upside, is something that we can directly measure and is directly related to issues of valuation. So we'll often want to think about forecast accuracy, weighting things by their financial importance, not just taking an equal weighted average across all possible kinds of errors. We might want to weight more heavily the kinds of errors that we're most interested in avoiding. Models don't stay the same. Models change. Models need to be replaced. So we want to think about what kind of model evolution we might expect. We can have static parameters that stay fixed, or we might think about having adjustable parameters that maybe we change over time. We might think about models where when we see errors, we update our parameters so that we can make gradual changes to our model as our data set increases. As we make more observations, we can improve our estimates of parameters, and we may need to think also about identifying situations where we would declare our model to be broken. There's some fundamental change in the market, sometimes called a regime shift or a break in time series, that's telling us, hey, that model's not working, there's something new generating the data. Okay? Someone swapped out one roulette wheel for us and they put in another one. So those are kinds of things that we want to be aware of. There's a question, is the model completely static? Is it somewhat dynamic where the parameters get updated? And if so, how and when? And then when is it time to go shopping for a new model? How do we set up forecasts? Well, typically we start with observations up to some particular time t. Now, we can't really go from the infinite past, and hopefully none of our results would depend on the series existing in the infinite past. But what we usually think about for forecasting is there's some amount of history up to a particular point, and maybe we have some set of observations, x0, x1, x2, x3, up to the time xt, and my convention for forecasting will be t will be the time at which we're making our forecast about future values for t plus 1, t plus 2, all the way up through t plus h, where h stands for the horizon. And we assume that we have the information set available of everything that happened before, and possibly including the current observation, and we want to know what happens next. The probabilities that we're interested in computing are going to be conditional probabilities, but it's really the same thing we've already seen. We're taking expectations. The only difference is we need to look at the time index and not apply stationarity directly. We can apply stationarity for things that are random variables. That is, we can say that the probability distributions of future realizations are the same, but that does not mean that past draws from the distribution are the same. Okay? Even though a head and a tail are equally likely, or one of the 6 sides of a die are equally likely, on our next 5 random occurrences, the last 5 are fixed because they are what they are. So that's our distinction between past and future. We can look at making point forecasts, and we can think about whether we can have enough information to generate a full probability distribution for future events, or perhaps somewhere in between, not just a number, but perhaps moments of the future distribution. What's the mean? What's the variance? And that could tell us something about what our confidence is and what a confidence interval is around a forecast for future values. We can sometimes include subjective information as well in a Bayesian approach, where we take information about what our prior beliefs are as a starting point, and then we iteratively update our forecasts as new information becomes available, and we do it in a way that's consistent with the laws of probability. The optimal forecast we can think of from a result of Granger as simply being the forecast at horizon h is the conditional mean of the forecast. That's our best forecast, provided that the cost function is symmetric and convex. So this says that the forecast for a future variable is we take its expectation based on what we know now. We can also compute other moments around it, but for the point forecast, this is the best forecast that we can do in terms of minimizing different error criteria. So for a given model, we can use the optimal forecast. And for a given set of data, we're tasked with finding what the optimal model is. If we think of a typical kind of random walk, in this case an arithmetic random walk, where I have a price at each time is the previous price plus some new innovation, some new event that comes along, some with step size sigma, where z is a normalized random variable, sigma is the scale of the volatility, and we ask, what's my forecast h steps ahead for the value of the price that follows this forecast? What I do is I iterate this out to solve for p t plus h in terms of the previous t's. I take expectations, and because all I'm going to do is add together more z's, and those all have zero mean, the expectation of p of t plus h, given the information I have available, is the current price. That is, the forecast for the price h steps in the future is the current price. Now for a symmetric random walk, that makes sense. We're equally likely to have the z's go up or down. They will in general diffuse. They will move around. They're very unlikely to be exactly back where we started at p. Nevertheless, that is the optimal forecast. So we want to think about ways of measuring deviations from forecasts because our forecast is unlikely to be exactly realized, and therefore we define forecast error to be simply the difference between our forecast and what happened, between the outcome and the prediction. If we said the price was going to be 100 and it turned out to be 200 or it turned out to be 50, the difference between the forecast and the outcome is the error. And a good forecast is not one that gives you the highest price. It's the one where the prediction comes closest to the final outcome. So if we define our forecast error with E to be the outcome in the future minus the forecast that was made at an earlier time t, so this is the forecast made at time t with horizon h. And what we want to compare it to naturally is the observation at time t plus h. We can't do that until we've reached time t plus h or beyond, but at that point we can evaluate the forecast and the forecast error. So we can take this difference. Now we want to then define the error function. A cost function is something that we'd like to minimize if we have good forecasts, and something that we can use to quantify or compare different kinds of forecasts. We'd like to say that one forecasting methodology is better than another if it produces smaller forecast errors. The most popular metric is the mean squared forecast error. So let's just take a look at the squared forecast error for a moment. If we take this quadratic form where we take the error, this error term, and we square it, and we might multiply it times some scale coefficient, a positive number c, for our cost. This gives us a couple of properties. First, it's 0 when the forecast is spot on, and it's symmetric. It treats whether we're too high or too low as both being errors. Now, a lot of times financially, we don't feel equally the same about losses as we do about gains. If we expected to make $1 million on a particular investment and we make $2 million, most people wouldn't count that as being an error. But we should, and the reason that we should is because it bears on our ability to make better predictions in the future. If we ignore the errors that are on the upside, we're missing a chance to improve. However, if we have some control over the distribution, if there are some observations and data or control over the distribution of our errors, we certainly can say that we'd like to have a forecasting methodology that minimizes downside errors more than upside errors. And in that case, we might want a cost function which is not symmetric, which doesn't have this simple form. So this is here for convenience, not because it's a universal answer to different kinds of applications. There's another problem with squared forecast errors as a criterion for choosing or evaluating models. And we can see that by doing the same calculation in two different ways. Here's an example. Consider the AR1 process. So if we think of demeaning our variable, we could write this as xt is minus lambda of xt minus 1 plus sigma z, or here I've just written it as epsilon t. Now I could also write, just by subtracting xt minus 1 from both sides of the equation, I could write an expression for delta xt. And I could forecast that. That is, instead of thinking about a forecast for x, I could forecast how much x changes from one period to the next. Obviously, those are exactly the same thing. So let's take a look at whether we have a process described by levels or by differences. So at one step ahead, the forecasts differ. So we just compute by taking expectations. So let's let f represent the forecast of our usual model, and our usual expectation of x of t plus 1 at time t, given the information it's at time t, is minus lambda xt, the previous value that we had, the last value that was observed. And for our delta, we get minus 1 times 1 plus lambda xt. But that's not surprising. They're different variables. We would expect the forecast quantities to differ. And I've denoted the delta one with a prime. So f prime is for the differences, f is for the levels themselves. Now, what about the forecast errors? Well, the mean forecast errors in this case are identical, which tells us that at this level, it doesn't matter which one we're using. The errors would be the same. And if I minimize the errors, forecasting technique or parameter estimation, I'm going to get the same result in either case. So in the first case, I apply my definition for the forecast error, observation minus forecast. Once it's known, this would be the forecast error, but we're going to ask about it in expectation before it's yet known. So we'd like to minimize our future errors. Once they're past errors, it's too late to do anything about them. So here's what we do. We construct this object, x minus f. We take its square and we compute its expectation, and we do the calculation and we find it's sigma squared. We do the same thing with f prime, and its future value, delta in this case of xt plus 1, the value that we're trying to forecast, we find we get the same value. But at 2 steps ahead, things are different. At 2 steps ahead, we can do the calculation again in terms of both variables. In terms of xt, the algebra is a little bit longer, but it's straightforward. It's the same rules that we apply. We have xt plus 2 by doubly recursing and doing a double substitution to get an expression in terms of xt, which is known, and 2 random variables for time t plus 1 and t plus 2. We compute the forecast 2 time steps ahead. We get lambda xt, lambda squared xt, and we compute the mean squared forecast error for the 2 step ahead forecast. And we find that it's equal to lambda squared 1 plus lambda squared, sigma squared times 1 plus lambda squared. And you should check and rederive this yourself. Now, in terms of the difference variable, we get a different result. So if we do the same thing for f prime at 2 steps ahead, and we do the substitutions, we have this expression for our expectation, and we compute the difference between the forecast and the outcome, and we take its square and we compute its expectation. That's our mean squared forecast error for the expectation of the squared forecast error of a forecast system built using differences. And we do the algebra, and when the dust clears, we find that for general lambda, except for one special value, if lambda happens to be equal to minus a half, this expression differs from the one we found here. That says that the forecast criterion is different depending on which way we describe things. But that's not all. If we don't know our parameters, and usually we don't know the exact parameters, usually we need to estimate parameters from data. So if we're making forecasts using estimated parameters, we have an additional source of error. One of them is the underlying randomness. That's part of the nature of our process. But the other source of error is the fact that our parameters might not be right. And we can see that by putting in lambda hat for our estimate of the parameter. And of course, Lambda hat is not the true lambda. The process evolves according to the true lambda, but our forecast is made using our best estimate of lambda, which is lambda hat. So the forecast error in this case has a new term that depends on lambda minus lambda hat. It vanishes in the event that we have estimated the parameter correctly, but otherwise we have an extra term. We go through, we turn the crank, and you can check this, and what we find is that now there's a new term in the two-step ahead forecast error, which depends on the difference between lambda and lambda hat. So this extra term is an additional contribution to error when our parameters might deviate. And in terms of the difference variable, we get something else, which is even more complicated, which has even more terms. But one of the things we can check in both cases to make sure at least that we haven't made a terrible mistake in our algebra is to check that it vanishes in the case where lambda is equal to lambda squared. So we see that the mean squared forecast errors differ. They depend on the value of the parameter. They depend on the value of the estimate that's used in the forecast. And when we are comparing forecasts, we should make sure first that we do things that are invariant, that don't depend on the way we chose to label our variables to describe exactly the same thing. More importantly, we should think in financial terms. We should think about assigning error functions or cost functions based on the scenarios of interest. So again, we might not want to treat asymmetrically gains and losses the same way. Sometimes we might if we want symmetric precision, but it really depends on the setting. And it's something that you should keep in mind, and it's a choice of the modeler. There isn't a single right way to do things. Let's look at another setting for random walks, the binomial tree model that's used in option pricing. In the binomial model, in each discrete time step, a stock price, let's say an asset price, can move only up or down to a particular fixed value. This sounds crazy far away from reality. Stock prices can move anything up or down in very small increments. But in this model, we say there's only one thing it can do going up or down. And typically in the model, we allow the movements to be by the same percentage increase, to have the same return in each time step, so that it's a stationary series. So here's the structure of the model. Time goes to the right, and in each column, so I start from this point here, and I've labeled all these nodes, and I go either to node 1 or node 2, and then from each of these other nodes, I have two choices as time evolves. Here I can go to either 4 or 5. I can go up or down. If I'm from 5, I can go to 8 or 9. If I end up at terminal node 8, though, there are a lot of ways I could have gotten there. I could have gone 0, 1, 4, 8. I could have gone 0, 2, 5, 8. I could go 0, 2, 4, 8. So if I want to know what the likelihood is to end up at a terminal node of a particular value, I can just add up all the possible ways to get there, multiply times the probability of seeing that particular path realized. And that turns out to be essential for doing option pricing and for managing risk. But in terms of the basic model, we recognize right away that's a random walk. After all, we're taking steps, discrete steps in each time period, and we're looking at the aggregate behavior of those steps. And we know that some of the large time properties are related to the statistical distribution of the sum of random steps. So we do this in two steps, no pun intended. We build the tree, we have a structure for what the up and down moves represent. Usually we have a fixed return associated with up and down, and that gives us a recombining tree where you notice there are two different ways to get, say, to node 4. Going up and down is the same as going down and up. There are trees that don't necessarily recombine, but in this case we'll keep the recombining tree. And there are trees also that have multiple branches. There are trinomial trees and multinomial trees. But we'll look at the binomial tree. So first we have the tree structure. We assign to each branch a magnitude by which the return changes, if we go up or if we go down, and a probability of that happening. Once we set up the tree structure, we're ready to do some analytics and to price derivatives on this tree, and also to take a look at, in this structure, some very interesting possibilities for exotic options and for different boundary conditions. So the random walk process is the basis of one approach to option pricing. And it's obviously an extreme simplification of the dynamics. But in the limit, we actually end up getting exactly the same result that we do through continuous time approaches. So in each time step, the underlying can either go up or down, and we have uncertain payoffs. Usually in this model, we think of having two assets, one risky asset and a risk-free asset, whose return doesn't depend on where we are on the tree. But one of the things we also need to do to match this to reality is take our abstract random walk and put some parameters on it. We need to find out what the appropriate scales are. And so we need to set the scales, we need to decide on the returns, we need to decide on the probabilities, and that's going to tell us how this can map over into the real world. So here's an example of how we set up the structure. We have a recursive behavior for a random walk where we say at each time step, the new price, one step ahead, is going to be the previous price either times a number I'll call u for an up move with probability p, or a down move with probability 1 minus p. That's one reason why I sometimes use s instead of p for probability. S we'll think of as stock price. So the structure has this tree structure here, where as I build things up, I start at this node with price S0. With probability P, I can go up and realize a price S naught U. If I go up again, the probability of going up and up is P squared, is my cumulative probability to get to this point. If I do so, the asset price with probability P squared is going to be S naught U squared. Now, I could end up, if I have an up and a down move, I have two different ways of doing that. Each of those ways has probability P times 1 minus P, and I get this value. And similarly for the downside of the tree, and I can go at an arbitrary number of steps. So what's the structure we expect? Well, it's a binomial tree. No surprise, we find a binomial distribution. The probability of observing a particular stock price is equal to the probability of our binomial distribution of the corresponding set of up and down moves. So I have t, in this case, if I have t time steps and I need there to be k up moves, I have t choose k ways of doing it. They have probability p to the k, 1 minus p to the t minus k. It's our old friend, the binomial distribution. Let's look at a concrete example. Suppose u is equal to 2. This is rather extreme. Suppose in each time step, the value of the stock doubles. Suppose if I go down, the value of the stock is cut in half. Suppose the probability of an up move is 1/3. The probability of a down move is 1/3. Excuse me, probability of up is 2/3. Probability of down move is 1/3. And let's suppose we have a starting price of 16. So the tree looks like this. 16 with probability 2/3 doubles at time 1 to value 32. And it can double again to value 64. The probability of getting there at the end of 2 time steps is 4/9. The other terminal values at t equals 2 are 64, 16, and 4. And that's it. It can't be anything else. All right. So this is a very rigid model of how stock prices could evolve and what their terminal values are. We can do some of the usual analytics. For example, we could ask about the distribution of stock prices at time t. And here we have it. So these are, probability 4/9 to get a 64, probability 4/9 to get a 16, probability 1/9 to get a 4, and that's it. Now, where it really gets interesting is when we apply this to option pricing. Now, option pricing, options are a kind of derivative, and a derivative is a security whose value depends on another security. So you may be familiar with stock options, and in particular call options, that give you the right, but not the obligation, to buy a security at a fixed price K for a call option, but you would only exercise that if the market price is above K. So if I tell you you have the right to buy a stock at $10, You would not exercise that if the stock were $3. You'd only exercise it if the price were more, and then you could realize an immediate profit. So if you have an option to buy a stock at a strike price, K equals $10, and at the time when the option is about to expire, if the stock price is $64, that means you could buy it for $10, sell it for $64, and have a profit of $54. So no arbitrage tells us that if you could make that $54 by doing that transaction, then the value of the option should be $54. So if we put options work similarly, they give you the right but not the obligation to sell at a fixed price. You're not going to sell if you could get more money by selling at the market price. So put options are valuable if the price goes down. Call options are valuable if the price goes up. But in both cases, their value depends quite asymmetrically on the value of the underlying, on the value of the stock. So a common structure that we see in binomial trees as part of our approach to option pricing is that first we set up the binomial random walks that correspond to the stock price movement, and then we look on the terminal nodes out here, in this example at t equals 2. I'm assuming my option expires at t equals 2. I look at the terminal nodes and I say, what are the values of the options on the terminal nodes? And they're determined by the value of the stock on the terminal nodes. So if the stock has values 64, 16, and 4, then the value of a call option, C, at that point in time, could be 54 in the upper position with probability 4/9. It could be 6 with probability 4/9, because there are two ways of reaching it. Or it could be 0, because we're not going to buy a stock for $10 if we could buy it by exercising our option. If we could just throw away the option, it's valueless, and we were to buy the stock on the market for $4. Put options work in a complementary way, and there's a property called put-call parity, which you can see here in action, where when the risk-free rate is 0, the value of a call minus the value of a put is the value of the security minus the strike price. So here we have the put is worthless up here because the stock is worth more than $10. Here it's worthless, stock is worth more than $10. And down here it's worth $6 because we could sell for $10 something that we could buy for $4. The tree becomes useful for more general kinds of problems, and especially if we have different kinds of boundary conditions. So typically we're thinking for a vanilla option that only expires at a particular point in time, we go out and we look at the terminal nodes in the tree. But we might have dividends that occur at some intermediate point. We might want to know at intermediate points on interior nodes of the tree, should we exercise the option? Is it advantageous to do so? There might be exotic options that if we hit a particular node, if we go down too far before we going up, the option might become valueless. Those are known as knockout options, and they're knock-in options that start valueless, but if we hit a particular node, then they come to life. And that splits, it differentiates among the different paths. We don't just group them together and count the total number of combinatorics. We need to separate those that might pass through a particular node from those that don't. So usual it reduces to problems that we've already seen in probability, where we need to classify different kinds of trajectories, compute the probability of each, and then sum up the ones that are of interest for the particular application. Now, to be able to connect with our previous model, what we need to do is calibrate the tree. We need to be able to connect parameters on the tree with parameters of real-world stock prices. So if we think of our stock price as having a random walk with a logarithmic return variable that takes binomial steps, in this notation, if we think of R as being defined as a logarithmic return, then in the binomial model, R would take two values, either the logarithm of u, so that e to the r multiplies st minus 1 by u, or logarithm of d. So that's straightforward. If we want to know how to implement our model, and we have a given u and d, this is how we do it. And we can also do it in terms of typical Bernoulli type variable. If we let x be 1 or 0, we can construct a variable. Because it only has two states, it doesn't really matter how we do it. We can rewrite things through linear transformations as long as there are two different states. Here, if I have a 1 and a 0, I can multiply something and add something else, and I can relate it to the log u and log d formulation. So we can use different kinds of formulation. The basic point is it's a two-state model at each node. So to connect this to real-world asset values and their returns and their volatilities, we calibrate the model by taking expectations. So we would calibrate mu to be the expectation of r from the formulas that we had before, and we compute sigma squared as the variance by applying the definition and using our usual results for things that are constructed out of basic z's. So we put in the distribution of our binomial variables, we have some extra parameters, we compute, and then what we're going to do is we have expressions now for mu and sigma squared, which are things that we can estimate and think about in terms of real-world asset prices, their mean and their variance, and we can connect them to model parameters in the random walk, things that are the step size, A and B, the coefficients of the step formulation in the Bernoulli form I just showed you, and P, the probability. So we can solve for A, P, and B in terms of the up and down factors, for example. And we can do that like this over here to have A and B in terms of those with mu and sigma. And then we can express log U and log D also in terms of mu and sigma, so that if we have particular real-world values of mu and sigma, that can tell us what U and D we can use on the model that will give us something that will be a discrete representation of the real-world drift and volatility that we want. Notice that the specification actually matches different numbers of parameters. That in this case we have two real-world parameters, mu and sigma, in terms of three model parameters, three unknowns. There's a problem in the classical probability literature known as gambler's ruin. That's a discrete time stochastic process that's solved in a different way, and it would be interesting for us to take a look at it. So here's the idea. The idea is, suppose that you and I are gambling, and we begin with the total amount of wealth, total amount of assets, let's call it A. And in this example on the right-hand side, imagine that there's $10 that we have between us, and then we start with you have $5 and I have $5. And the idea is we play a sequence of games. At each step, if you win, you get $1. If I win, I get $1. The total amount of wealth is conserved. And we play until one of us is ruined. That is, until either your capital goes to 0 or mine does. So from your perspective, either you get all the wealth or your wealth goes to 0, at which point it stops. Now, I've shown on the right a picture that illustrates some possible ways this game might come out with these starting conditions, and each color represents a different path. You'll notice that of the 5 paths that are shown here, 3 of them finish with the player winning, that is, capturing all $10 that are available. 1 of them finishes with ruin, that is, at $0, and then it stays there. Once you're ruined, you're not allowed to make any more bets. In the green path, 1 of them has not yet hit either end. It hasn't yet hit 0 or $10. And we might even wonder if it could just keep going indefinitely. So in this kind of game, we have a repeated set of gambles. And to keep it general, we're going to allow the probability of success or failure, Bernoulli trials, be asymmetric. So let's let P represent the probability of success. Q is 1 minus P is the probability of failure. You start with some initial capital, x greater than 0. And we have these two classic stopping points, which are either when your capital X is equal to 0 or X is equal to A. Now, there are two kinds of things that this typifies, two classes of problems known as stopping problems and boundary problems. The boundary case is pretty obvious. We have these two cases where our wealth either hits 0 or it hits A, at which point we stop. So we can ask, unlike our previous case where we looked at time series and just said, we give initial conditions, what happens in the future? Here we have boundary conditions that specify something specific that occurs if and when we hit them. And of course, there are obvious financial applications. These are things that represent bankruptcy. That's the classic definition of ruin, but they might be other events. For example, hitting a capital reserve requirement, hitting a credit default trigger, hitting a stop loss limit. And we could think of things on the upper limit as well. We might have a strategy where we terminate an investment once we reach a desired goal. The stopping problems are a little bit different. Those are cases where we want to know, does a given process stop? Does it ever reach the condition? And if it does reach the condition, what would be an expected time, or what would be the distribution of stopping times? We might also think about this strategically. We could have a question where we ask, what would be the optimal way to, say, run a business if we wanted to minimize its default probability or its bankruptcy probability? So let's look at the math and see how we can do this. What we'll see is we have a recursion relation, but this recursion is not in time. This recursion is in money. So here's what we do. Let's let Q sub x denote the probability of ruin, that is the probability that will eventually hit 0 before x equals a, starting from an initial capital level x. Now the interesting thing here is it does have a Markov structure, because it doesn't matter what's happened in the past. All that matters for our probability of surviving is how much capital we have at the present time. Probability is obviously conserved. So the probability of ruin now, we can relate to what happens after our next game. After the next game, we could win with probability p, in which case our capital would be x plus 1, and that would give us p times qx plus 1. Or we could lose and end up with capital X minus 1, in which case this would be our probability of ruin. And adding together these two mutually exclusive possibilities gives us our original probability. Now you can see that this is a recursion relationship in X. This kind of difference equation, where we have a relation between x minus 1, x, and x plus 1, is similar to differential equations that are second order. This is a second order difference equation. Like the differential equation case, there are two independent solutions, and we fix the boundary conditions by we fix the final solution by imposing boundary conditions on a general linear combination of the two solutions. So there's a special case when the probabilities are equal. Let's do the general case. In the general case where p is not equal to q, you can check by substitution that these are two different solutions. One of them is the trivial solution, that q sub x equals 1. And that's not an interesting solution to our problem, saying the probability of ruin is equal to 1, because we start out not being ruined. But mathematically, leaving aside the boundary conditions, it does solve this equation, because p plus q is equal to 1. The other one is this form here, q over p to the x, and remember q is equal to 1 minus p. And if you substitute this into the equation, you can check that it works. Now, therefore, the most general solution is a linear combination of these two special solutions. So we have two constants, let's call them a and b. So our general solution is of the form constant plus another constant times q over p to the x power. And we fix a and b by imposing boundary conditions. Two obvious boundary conditions. When x equals 0, we are ruined. If we have no money, the probability of ruin is 1, because we're already ruined. And similarly, if we have all the money, if our capital is equal to a, our probability of ruin is 0, because the game has already ended. So if we impose these, we can solve for a and b, and we get this result for the probability of ruin, this expression in the box down here. This tells us, as a function of a, x, and p, what our probability of ruin is, starting from any given level of capital X. Now, we can ask a variety of questions about what happens under these absorbing boundary conditions. For example, we could ask, can the sequence continue without terminating? That is, does the probability of reaching neither x equals a or x equals 0 in an arbitrary amount of time, is that some positive number? Is it equal to 0, which would mean that we do hit one of the other two boundaries? We could ask what the expected time is to hit. If we allowed ourselves to stop differently, what kind of strategy might we employ, and could we do something better? How do we take advantage of unequal odds? For the case where the odds are equal, we can do it in one of two ways. We can either check that 1 and x over a are special solutions to the equation, or we can take the limit where q approaches p using L'Hopital's rule and just taking our general solution. What do we see about actual numerical values to get some intuition about what's going on? Well, one interesting fact about this is that if we start very close to taking all the money, we have a good chance of winning, which isn't surprising. For example, suppose that there's $100 between us and we start with 99 and we're playing the house, and suppose the odds are equal, then you can check by the previous formula. We have a 99% chance of winning one more dollar before we lose all 99 that we have. Not surprising. We're close to owning all of the money. But what's less obvious is that if the odds are against us, we still have a very good chance of winning all the money before we lose what we have. That is, even when the odds are stacked against us, if we have sufficient capital reserves, the odds of attaining a finite goal, and in this case a relatively modest goal, can look very attractive, even when the odds are against us. So if the odds are against us, we typically think it's a game that we shouldn't play. The expected value is negative, stay away. We want to look for opportunities where we have positive expected value in a gamble, and furthermore, where we have adequate compensation for risk. If the expected return is negative, normally we would say, let's leave it alone, provided there are some other better opportunities available. But all that changes when we limit our objective and we say, suppose I only want a fixed amount of money and I'm not going to play the game indefinitely. In fact, we can go a bit further. Not only does this sometimes give us a positive chance for achieving a goal before we get ruined, but it says that when the odds are against us, sometimes we should take even more risk. What if we change the stakes? Suppose we increase the bet size from 1 to b, and let's suppose that b evenly divides a and x, just for simplicity. So if we change our bet size, then we update our recursion. The problem has the same structure, it's just the individual steps are chunkier. When we substitute in, we play the same game as before, we solve for our formula, we get a new result, and what we find is that when the stakes are increased, that if the odds are against us, we have a lower ruin probability, that is a greater chance of winning all the money and hitting the upper boundary than we did before. So if the odds are against you, it can be advantageous to swing for the fences, so to speak. That is, you can think of this as being intuitively as being kind of a complement to the law of large numbers. In a game where we play indefinitely, we know that our expected return is going to be negative. We, of course, need to worry about the fluctuations. But this says that if there's a definite stopping point, the fluctuations can be to our advantage if we stop when we get a fluctuation that's sufficient for us to hit our upper boundary. That is, the longer we play, the more likely we are to grind down and end up ruined. But if we take larger bets, we're more likely to have an instance where we hit our upper boundary. So lower ruin probability means greater overall chance of success. What if our appetite for risk is unbounded? That is, suppose that A is infinite and we want to keep playing and just see how much money we could get. Well, it's pretty clear that if the odds are unfavorable, that we're never going to get all the money. We've set ourselves an impossible task. And in fact, our probability of ruin goes to 1. In the case where the odds are in our favor, we can compute what the ruin probability is and get something potentially that's less than 1. How long does the game last? Well, we could ask about its expected duration in the same way. But now things are slightly different because now we have a generalization of our previous equation, but now we have an inhomogeneous equation. So let d be the duration of the game. then d of x plus 1 is the duration of the game starting from x plus $1, and dx minus 1 is the duration of the game starting from x minus $1. And we need to find out what d of x is, that is, what's the expected return as a function of x. So in our recursion, before we equated this to what's on the left-hand side, but now we know that these are related to one more play of the game, so we add 1 on the right-hand side. So instead of the previous homogeneous equation where every term involved a d, here we have this plus 1. You can check that this gives a solution to the equation. Here it's a slightly more complicated formula. For p not equal to q, for p equals q, this simplifies into a nice quadratic form, ax minus x squared for p equals q. So that tells us that, for example, in a fair game, if you and I each start with $100, $200 total, the expected duration of the game is 10,000, 100 times 100, and it grows as the square when the stakes are equal. So let's summarize. Gambler's Ruin is a problem which has a recursive structure. It's a discrete time process in money rather than in time, and it's subject to boundary conditions. The boundary conditions tell us when the process terminates. It's got applications to gambling, obviously, to insurance, where the ruin problem in the insurance literature is finding the probability that you have adequate capital to never get ruined by random processes which represent the arrival of insurable claims or losses. It has applications to thinking about bankruptcy likelihood, to credit default, and to bet sizing in investment strategies or in gambling strategies. The stopping problems that we consider are things that could be defined by economic conditions, such as a company in distress meeting a particular term in a covenant, or a bank loan being called subject to certain terms. We can think about optimal stopping problems where we might have different kinds of objective functions. Rather than maximizing expected return, rather than thinking of maximizing Sharpe ratio, we might think of a business venture where what we'd like to do as business owners and investors and entrepreneurs is, sure, we might like to maximize our profit, but maybe what we'd really like to do would be to maximize the lifetime of our business or minimize the probability that we go bankrupt. And those will not be exactly the same calculation.